In this video, we're going to take a look at how to calculate value of a three-dimensional object using the disk method. So here's the problem. We are going to create a three-dimensional object. We're going to start out with a closed bounded region in the plane, and then we're going to create a three-dimensional object by rotating that region, that area, around either a horizontal or vertical line. Once we do that, we're going to create a three-dimensional object, and we want to find the value of that figure. So I'll take a visualization of this problem. Basically, we're going to have a curve in the XY plane, and then we're going to wrap it around the x-axis or wrap it around the y-axis. In this case, I've wrapped it around the x-axis in this visualization. Let me show you what I've done here. So first off, I start out with the standard Cartesian coordinate plane. And I'm going to have the graph of f of x equals x squared. Let's say we want to find the area of the region bounded by this, along with the x-axis from 0 to 2. So we want to find the area of this region. Well, in a previous video, we found the area. Now what we're going to do, so we'd create this area, we didn't integrate, we could find this area through integration. Now what we want to do is we want to wrap this area around the x-axis in a circular way. So I'm going to have to turn to a three-dimensional graph to see that. So here I have the XY axis, but I have in 3 dimensions. And if I start rotating this area around the x-axis, what happens is I've created this three-dimensional object. Now this object looks like, I don't know what it looks like, but it looks like a cap. But as you can see, as I pull it around in 3 dimensions, it's a solid three-dimensional shape. And I want to find the volume of that. So I want to find the volume of this shape here. So that's the problem that we're looking at. We start out in 2 dimensions, we find some area of a closed bounded region, and then I'm going to rotate that area around the x-axis or the y-axis or some other horizontal line or some other vertical line. The way we do this is we do this in a way that's similar to the Riemann sum where we found the area. So we basically cut the rectangles in the region that are perpendicular to the line of rotation. So we're going to approximate our area by using the rectangles from the standard Riemann sum. But then when we rotate those around, a horizontal line or a vertical line, the rotation of a rectangle all the way around a horizontal or a vertical line is going to give me a disk. If I take the limit as the width of that disk goes to 0, then we get a Riemann sum. And so when we take the limit as width goes to 0, those Riemann sums are going to turn into integration. And the formula for that integration is going to look like summed up volumes of a disk. Now, the volume of a disk is pi r squared times the width, or pi r squared times the height, depending on how the disk is oriented. And then we're going to sum all those up, and I'll get a formula that looks like pi r squared times h, or pi r squared times w, where the w is going to turn into my dx as I integrate. The h is going to turn into my dy as I integrate with respect to y. And the radius is not going to be the same for each one. So let's go back to this example here. We were going to rotate around the x-axis. So I'm going to split this area into little rectangles. And so the height of each rectangle is going to be determined by where the curve is at that point. And so I get a rectangle like this. And if I rotate that rectangle around the x-axis, what I've just created is a disk. Now, a disk is just a cylinder, so the volume of the cylinder is going to be pi times the radius squared times the width of this disk, or the height of this disk. What we're going to end up doing, like I said, all of the the radii for each one of this, so the radius for each disk is going to be determined by the height of where the curve is. So right here, the radius goes from the x-axis up to the curve. Down here, if I had a disk down there, the radius would go from the x-axis up to the curve, and it'd be a lot shorter radius. Out at 2, the radius would go all the way up to a 4. So the height of, or the radius of my disk is determined by height of the curve down to where I'm rotating it around. And then I'm going to let the width of the disk get smaller and smaller, and I'm going to add up more and more and more disks. And as I add up more and more disks, they'll take the space up, or they'll take the volume up of this bigger object. So imagine lots and lots and lots of little disks in here. I keep calling them disks because we use the disk method, but it's really a cylinder. So hopefully that makes sense. Oftentimes when I'm doing this, what I'll do is I will draw this in 2 dimensions, and then I'll rotate it around just in my head. So I'll draw the area, and then I'll draw one rectangle in there as kind of a demonstration rectangle. So oftentimes that's what I do when I draw it. So oftentimes I'll draw it in 2 dimensions, and then I'll just draw sort of, oops, I can't draw very good today. I'll draw a rectangle that is representative of all of the other rectangles. Again, that wasn't very good. Now, when I drew this on Desmos, notice that my rectangle was essentially perpendicular to the line of rotation. The line of rotation was the x-axis, which is y equals 0, and the rectangles were vertically oriented. So my volume of each disk that was created is pi r squared times a width. If I would have rotated a region around the y-axis or some other vertical line, then it would have been a height rather than a width. And I'd be integrating with respect to y when I took the limit of that Riemann sum. Here, I would be integrating with respect to x if I took the limit of the Riemann sum. So as the width or height gets smaller and smaller, I take that limit, the widths go to 0, and it turns into, the Riemann sum anyways, turns into an integration. So if we are in a situation where we are rotating around a horizontal axis of revolution, then the volume using the disk method can be found by pi times the integration from a to b of a radius squared. That radius is going to depend on what value of x we are at. So we call it capital R of x. But again, this is pi radius squared. You don't see the width because the width turned into a integration with respect to x. And if we have a vertical axis of revolution, then we integrate pi times radius squared, but with respect to y. So my radius is going to depend on the y values. And when I integrate from c to d. Those are going to be y values. So if we have a horizontal axis of revolution, then the radius is going to be determined by the x values. We're going to integrate with respect to x. If we have a vertical axis of revolution, my radius is going to be determined by y values, and we're going to integrate with respect to y. Now again, pi r squared. So just think pi r squared, that's the area of a circle. And then the height part is taken up by the integration with respect to y. In this case, the width part will be taken up by the integration with respect to x in that case. But these are the two formulas we're going to use for the disk method. And we're going to use those over and over again. So let's do an example. Let's find the volume of an object made by revolving the region bounded by y equals 4 minus x squared, x equals 0, and y equals 0 in the first quadrant around the x-axis. I'm going to draw this region, and a lot of times I just sketch it out by hand. Because I have access to Desmos, I will actually graph it in Desmos. I'll graph the two-dimensional region and then kind of talk about what would happen if we revolved around the x-axis. So what I've graphed is y equals 4 minus x squared, or f of x equals 4 minus x squared. That's the parabola pointing down. And then y equals 0 is the x-axis. That's this purple line. X equals 0 is the y-axis. That's this vertical line. And if we're talking about the area, so now we have two bounded areas. One is over here, one is over here. It's stated that it wants to be the one in the first quadrant, so it wants to be the one that goes from 0 up to 2. So that's the region we're going to be revolving around the x-axis. Now, if we wanted to draw a rectangle, we could. I don't think I'll draw one right now, but you could easily draw a rectangle. And we're going to rotate that region around the x-axis, creating a three-dimensional object. We want to find the volume of that object, and we can use the disk method to do that. I guess let me just sketch what's happening here. Because I'm using the disk method, because we're rotating it around the x-axis, the x-axis is horizontal. And so the rectangles that we're going to use are going to be vertical. And the width of these rectangles are going to be with respect to x, done with respect to x, because we're rotating around a horizontal axis. So there you go. Now the radius of each disk is the same as the height of any rectangle. The height of the rectangle goes from the curve down to the x-axis, or y equals 0. So from the curve at the top of the rectangle down to the bottom of the rectangle, which is not x equals 0, y equals 0. The x-axis, which is y equals 0. So now we're ready to set this up. Now, before I go any further, I do want to point out a couple of things, and that is this region, as far as x values, goes from an x value of 0 all the way up to an x value of 2. So when I'm integrating, I'm going to be integrating from 0 to 2 in terms of x values. The rectangles were oriented vertically, and therefore we're going to integrate with respect to x. Again, we're rotating around a horizontal axis. Now, again, rotating around the x-axis is the y equals 0 line. That's going to be important in just a moment. Therefore, I'm using this formula. So the volume of my object is going to be pi times the integration from A to B. Now, what's A and what's B in this case? Well, A and B are the bounds on the x values. So A here is 0 and B here is 2. The radius, this is where it gets a little bit tricky. The top of that rectangle to the bottom of the rectangle determines that radius, okay? The radius is the height of each rectangle. So the top of the rectangle started at y equals 4 minus x squared. So we start at 4 minus x squared. And then we go down to the bottom is the x-axis, which is y equals 0. Now in this one, obviously we don't have to write minus 0, but in other ones, that we're going to see, it's always good to think of the radius as being top of the rectangle to the bottom of the rectangle. All right, or I misspoke. Top of the rectangle down to the line we're rotating it around. The line we're rotating it around in this case is y equals 0, so down to there. So that's it. Now we're ready to integrate. Make sure you have a square on the outside of this. Now, what I tend to do when I integrate is I tend to just use my calculator's integration feature and being able to use a definite integral on that. If you want to, you can obviously do this by hand as well. You just have to multiply out some polynomial and do some simplification. What you end up with is about 53.62, which is 17 and 1/15 times pi. So when you do the integration, you get 17 and 1/15. And then obviously you have a pi left. If you do the multiplication, that's approximately 53.62 rounding to 2 decimal places. It won't always come out to a really nice number times pi. Sometimes it does, sometimes it doesn't. Here, this is pretty nice. This rational number times pi. But that's it. That's the idea. Again, radius is top of the rectangle down to the line you're rotating it around. Just so we've seen the three-dimensional version of this, obviously this is the two-dimensional region that we want to rotate around the x-axis. If I want to rotate that around the x-axis, what we get is this three-dimensional object here that, almost looks like well, if you put it this way, looks like I don't know, Hershey's Kiss almost, or something weird. But that's the idea. All right, that's the three-dimensional object we've created. And we've seen that the volume of that object is approximately 53.62. So volume of that object there, about 53.62. Let's do another example. Now, in this second example, we're going to take the exact same region, but we're going to rotate it around a different line. In this case, we're going to take that same region, the one that's created by y equals 4 minus x squared, x equals 0, and y equals 0 in the first quadrant. And we're going to rotate it this time around the y-axis. Now, the y-axis is vertical, so when I do this, I'm going to have to start integrating with respect to y if I want to use the disk method. So let's rotate that region we looked at around the y-axis. So here's the region we're looking at. We want to rotate around the y-axis. Now, the y-axis is here, so we're rotating it around that way. If I'm rotating it around that way, and the disk method, I want rectangles that are perpendicular to the line of rotation. So my rectangles are going to look this way, and my rectangles are going to have width that are y values, okay? Or with their y values. Now the radius is going to go from the radius is going to be the length of that rectangle from the top where it hits my curve down to the line I'm rotating it around. And as you rotate it around, we're going to create a three-dimensional object. And again, the radius is the top of the rectangle where it hits the curve down to the line I'm rotating it around. So we know we're going to have to integrate with respect to y. One thing I want to point out is that because we are integrating with respect to y, we're going to have to use y values as our bounds. So in the previous example, we used x values from 0 to 2, but my y values range from y of 0 to a y of 4. So we're going from bottom to top of this region. So when I integrate, I'm going to integrate from 0 all the way up to 4. All right, so here's what we're going to do. The C is my lowest y bound, which we said was 0. My D is the highest y bound, which we saw was 4. The radius is going to be done with respect to y. So just like in the previous case, it was nice that I had y equals a function of x. In this case, my graph right now is laid out as y equals a function of x. I am going to have to, off to the side, rewrite that and solve for x. So if I subtract 4 from each side, I get y minus 4 is equal to negative x squared. Multiply both sides by a negative 1. That's going to be a positive 4 and then minus a y. And then it's a little bit troublesome to take the square root because remember we can take the positive or the negative square root. But what we can remember is that when we were looking at this region, it was the part of the curve in the first quadrant. So the first quadrant is going to be the positive square root. So that means if I want to write the curve, at least the part in the first quadrant, I can just say x is equal to the positive square root of negative y plus 4, or I'll call that 4 minus y. I'll call that 4 minus y. So again, I can take the positive square root because in the first quadrant, that curve has positive x values. So this is going to be the right-hand side of that rectangle, or what I would call the top of the rectangle. The bottom hits the line we're rotating it around. The line we're rotating around is x equals 0. Therefore, my radius goes from the square root of 4 minus y down to, let me put that in parentheses, down to x equals 0. So x equals square root of 4 minus y down to x equals 0. So we just write the expression from square root of 4 minus y down to 0. And then I square the whole thing, square the entire radius. Obviously, if I was doing this by hand, I would simplify by first not writing the minus 0 and then squaring a square root just gives me 4 minus y. And so we get some nice things there. Double equals, but so we get some nice things. if I'm trying to do it by hand. It's not really hard to do by hand. However, I tend to just integrate the way I see it. So I use my calculator and I take the square root of 4 minus y. Now, there's a couple of different ways you can do this with y's on your calculator. One is just use the variable key, and while the variable key is going to generate x's, as long as you put the variable key in every time you see your variable, you can do that. You can also use the alpha feature and do alpha and then use the y if you really like the letter y. But I tend to just use the variable key and just say this integration is the exact same integration if I would have changed all of my variables to x. And so when I type it in on the calculator, I type it in like this, even though I know those x's should be the letter y in reality. Now, when that's all said and done, either doing this integration by hand or doing it on your calculator, you end up with 8 pi as your final answer, which is about 25.13. So that would be the final answer for what is the value we get when we take this region and rotate it around the y-axis. Now, the most obvious thing is that rotating around a y-axis is going to most times give us a very different number from rotating it around the x-axis. And that's because we got a very different shaped object. When I took that region and I rotated around the x-axis, I got one shape. If I rotate that region around the y-axis, I get a very different shape. So we are going to get different values depending on the line we rotated around. So just to give you an example, remember that when we drew the f of x and we rotated around the x-axis, we got this shape. Well, when we rotate around the y-axis, again, this is the region in here. I won't shade it. I could, I guess, shade it. There, it's shaded. If I rotate around the y-axis, I get this shape. So again, a very different looking shape with a very different value. Okay, so we get this type of shape. Again, that's the visual. I'm trying to rotate that, but this parabolic type shape. Oops. Again, I'm graphing in 3D, so it's a little bit tough, but you can definitely see it's a different looking shape than what we had when we rotated around the x-axis. Here versus here. Let's take a look at another example, and let's use a different curve. Let's take the region bounded by y equals x squared, y equals 0, and x equals 2. That's the initial region that I graphed, by the way. And let's create an object by rotating it around the line y equals 0. The line y equals 0 is the horizontal line that is the x-axis. So that's what we'll be doing. Y equals x squared, y equals 0, x equals 2, that region, and rotate it around the line y equals 0. If you want to try this on your own, push pause on this video. I will do the problem myself in just a couple of seconds. I tend to sketch my graph as uh, every time I do this, at least the two-dimensional graph. Obviously, sometimes it's hard to sketch in 3 dimensions, but I usually just by hand do a sketch. Obviously, if I don't know what the graph actually looks like, then I might use my calculator to graph. But usually I just do this by hand. Obviously, it's hard to do on a computer by hand. So I'm using Desmos to do a sketch, and we have this parabola y equals x squared, and we're going to go from the x-axis, that's y equals 0 line, up to the x equals 2 line, that's the vertical line here. And then I'm going to rotate around the x-axis. Since I'm rotating around a horizontal line, my rectangles, I'll just draw a straight line here, are going to be vertical. Top of the rectangle is going to be at the curve. Bottom of the rectangle is down to the line I'm rotating around. And so we're going to get a radius that goes from x squared down to 0. That is y equals x squared down to y equals 0. So now I am ready to set my integration up. The bounds are going to be x bounds, and hopefully we went from x equals 0 all the way to x equals 2. That gives me one of my bounds there. So from 0 to 2, my radius is going to be, again, we start, the top of the rectangle is the top of our radius. The bottom of our rectangle is the line I'm rotating around, which is y equals 0. So that's what we get. And again, this is pretty easy to do by hand if you want to. But if you want to integrate with your calculator, you can do that as well. So we're going to take x squared minus 0 and then square it. That's just x squared squared. That's x to the 4th, which gives you 6.4 times pi. So the volume is 6.4 times pi, which is approximately 20.11. So that's the volume of the object that we have created. So we've taken this region, rotated around the x-axis. I don't expect you to know how to graph that using 3-dimensional graphing, but that's the object that we have. That's the object we saw earlier. And that object has volume, which is 6.4 times pi, or in other words, 20.11 approximately. Again, very different shapes than some of the other ones we've seen. Let's try one more. Let's take the same region, but instead of rotating it around the x-axis or the y-axis, let's rotate it around the line x equals 2. So that's the vertical line x equals 2, and we want to rotate it around that line. I always like sketching the region to start out with. If I'm rotating it around the line x equals 2, notice x equals 2 is one of the sides of the region. And that's a very nice thing. So we're rotating it around that line, and that means a representative rectangle with the disk method is going to have to be perpendicular. So it's going to have to look like this, which means I'm going to integrate with respect to y. Also, there's a couple of things to watch out for. One thing is that since we're integrating with respect to y, this region goes from an x, or excuse me, a y of 0, the lowest y value is 0, up to a highest y value that is 4. So the y values range from 0 up to 4. So that's where I'm going to integrate to and from. And then now you'll notice that the radius of a disk, which is going to be the length of this rectangle, is going to go from the curve, not down to 0, but instead down to x equals 2. Now you can go from 2 down to the curve or from the curve down to the 2. It's not going to matter because we're going to square that, right? We're going to take a radius squared. Technically, if I want a positive radius, it's 2 down to the curve because 2 is going to be bigger than these values on the curve. But you can subtract either way because we're squaring it. It's not that big of a deal. So that's the idea. That's the setup. And now let's do our integration. We're going to integrate with respect to y from 0 up to 4. And then the radius, again, I'm going to go from 2 down to the curve just to make sure it's positive. But if you wanted to do the curve down to 2, you'd get a negative value because 2 is a higher x value than these x values are going to be. So there we go. It doesn't matter which piece you start plugging in first because, yeah, it doesn't matter. I'm going to do my bounds first. These are y bounds. So my y bounds in this case went from 0 to 4. Now, the radius is tough because remember, we're doing this with respect to y. So I need to go back and solve this equation for x so I can get x is equal to a function of y. So I'm going to take y equals x squared off to the side, and then I'm going to solve that. Once again, the section of the region I'm looking at was in the first quadrant, so I can use positive x values. So I know that when I solve this, I can use x is equal to the positive square root of y. And that's not going to be a problem. So my radius goes from x equals the positive square root of y down to x equals 2. Or, like I said, square root of y is actually going to be smaller than 2 on the region between 0 and 4 when y is between 0 and 4. So if I want to call it a positive radius, I'll do 2 minus square root of y when I write it in here. So 2 minus square root of y, if somebody else would have put square root of y minus 2, it would not have been a problem because when you square it, you're going to get the same thing. So that's the idea. And now you can either do this by hand or you can just plug it into your calculator. I am going to plug it into my calculator. Make sure as you do that, the entire radius, the entire 2 minus square root of y gets squared and not just the square root of y part. So when I did that, I ended up with 2 and 2/3 essentially times pi. There was a little bit of a rounding error when my calculator did that, which is approximately 8.38. So that's what happens when I do this when I do this problem, when I find the value of this three-dimensional figure created by revolving this region around the line x equals 2. Again, when I actually did this integration with my calculator, I just put in a variable each time I saw a y, and in that case it was the x variable, but there we go. And when I did it with my calculator, there was a little bit of a rounding error. It should be exactly 2 and 2/3, but it was like 2 point, then lots of sixes, and then a 369. And again, that's because you're integrating close to 0 with square roots, and that tends to throw the calculator off. So there we go. I don't think we need to draw that figure. We've seen enough drawings of the three-dimensional figures that we've dealt with. Now, so far, every time that I've rotated a region around a line, that line has been one of the bounds of the region. Therefore, when we rotated, our disks have been solid. What if we revolve a region around a line where the line doesn't touch the region? So the line is away from the region. Like in the last case, what if I had revolved around x equals 3 instead of x equals 2? Well, then we'd have a big hole in our figure. And the disks that we would create would have space in the middle. So they wouldn't be solid disks, but instead those disks would have become washers. Now, the nice thing about washers is a washer is simply a disk minus another disk. So when we go to calculate the volume of an object, and that object has a hole in the middle, then it's going to be calculated by a washer, which is just a disk method minus another disk method. This is often called the washer method. The volume of an object that we create when we take a region and revolve it around a horizontal line, we can find by using a disk method minus another disk method. If you do this and you have the same bounds, A to B, then you can actually combine it into one big integration, although it looks fairly messy. So I tend to just say disk method minus disk method. I write these things in my calculator, and then it becomes pretty easy. Now, I want you to notice that the first disk method is going to have a radius which we call capital R. The second disk method has a radius which we call lowercase r. So we have two different radius. Each of them is going to go from some place down to the curve we're rotating around. So this is like the outside. The capital R is usually the bigger one. That's the outside radius. That's calculated by the outside curve down to the line I'm rotating around. This is the inside radius that goes from the inside curve down to the line I'm rotating it around. Let's look at a visual here. I'll kind of talk through one example, and this one is related to the first one we looked at. So let's say we want to take this region, and instead of rotating it around the line y equals 0, we want to rotate it around the line y equals -2. Well, if we did that, then there'd be a big hole in the middle here, and we'd get kind of a tube shape figure. Now, again, I don't expect you to know how to do this in 3 dimensions, but I've graphed this in 3 dimensions, and you get this shape figure with a big hole in the middle, okay? Now, each one of those rectangles that we started with now becomes a big disk. So let me draw at least part of that disk. So here it is. Here's the disk, and you can see that it's basically just a washer. It's a disk minus a disk. So what we're going to do is we're going to find volume by disk method minus disk method. And the outside radius in this case would go from the curve all the way down to the line I'm rotating it around. The inside radius would go from the bottom here down to the line I'm rotating it around. So the outside radius goes from the top of this disk down to the line I'm rotating, and the inside radius goes from the bottom of the region down to the line I'm rotating. If the line I'm rotating on is one of the sides of my region, then I don't need to do that like I did in examples 1 through 4. But if I'm rotating it around a line that the region is not touching, then I end up with these disks. So these disks with washer. So it's disk method minus disk method. Hopefully that all makes sense. And again, we're looking at the volume of this object here. The volume of, again, it's hard to zoom out enough, but the volume of that object is created by an infinite sum of disks like this, of washers, I should say, like this. So this is the thing we're looking for in example 5. We're going to take the region bounded by y equals x squared, y equals 0, that's the x-axis, and x equals 2, that same region we just drew. And instead of revolving it around a line that hits the region, We want to revolve it around the line y equals -2. Again, that was what I had drawn in my picture. Now, once again, I'm going to draw this in 2 dimensions as well, and then we'll solve this. So if I drew this in 2 dimensions, this is how I usually sketch it. Then there's my region. Now, as I said, we're going to think of this as doing a disk method where I go from the curve all the way down to the line I'm rotating around. That'll be my first radius. My second radius is going to go from the lower curve down to the line I'm rotating it around. So if I do the black rectangle minus the orange rectangle, that will, a disk method with the black rectangle minus a disk method with the orange rectangle, I'll get washers. And again, just so that we're all on the same page, we're rotating it around this line y equals -2. So let's do that. First off, the rectangles are perpendicular to the line I'm rotating. It's a horizontal line, so everything's going to be integrated with respect to x. My region's x values go from 0 up to 2. So we see that there's space in between. We know we're going to be integrating with respect to x. So we're going to do a washer method where we're doing the definite integral all with respect to x. The bounds here, lower bound on the x value is 0. Upper bound is 2. That's going to be the case for both integrations if I write it this way, because my region spans from 0 to 2 in both cases. Now, the larger radius, like I said, goes from x squared at the top, that is y equals x squared, down to the line we're rotating around. Now, the line I'm rotating around is y equals -2. So it's x squared minus a -2. If you want to call that +2, that's fine as well. It should make sense that you're basically adding 2 to x squared because we're making that radius longer by 2 compared to rotating it around the x-axis. Now my inner radius, well, that goes from the bottom of my region. The bottom of my region is determined by y equals 0 down to -2 again. If you want to, this one, again, they're all easy to integrate by hand. So if you want to, you can integrate by hand very easily. I typically use my calculator. Be careful with all the squaring going on. We get x squared, essentially +2, but that quantity is being squared. And so you get 25 and 1/15 times pi. When I do the integration over here, again, we're going to go from 0 to 2. That becomes a +2 squared. And we're integrating that with respect to x. So we get 8 pi So that's 17 and 1/15 times pi in the end. Now that is approximately, oh, I haven't calculated that yet. Sorry, that is approximately 53.62 once again. We shouldn't be alarmed about that. That was the same answer as we got from another problem, but a very different problem. So it's kind of interesting. When I say again, I just mean we got that answer way back at a different problem, but numerical answer. So we got the same numerical answer as a different problem, but that problem was not y equals x squared. It wasn't for this region. Remember that when we rotated this around the y-axis, or not the y-axis, when we rotated around the x-axis, we ended up with 6.4 times pi. And obviously this is much bigger than 6.4 times pi. The reason we're getting a larger value on this is because of the larger rotation. So in other words, if we look at this here, we get a much further rotation. So the volume is getting bigger as you move the line further and further and further away from the region you're rotating. So this distance is larger that you're going around. So as you move your line further and further away, the volume is going to get bigger and bigger and bigger. But that's what we get. So the volume of this object is, approximately 53.62. Let's do another example where we would use the washer method. Let's take the region bounded by y equals x squared, but this time also y equals 2 and x equals 2. And let's revolve that around the x-axis. So this region here is a region I have not dealt with earlier. So let's go ahead and draw it in 2 dimensions and then think about what would happen if we revolved it around the x-axis. So we're starting with the region bounded by y equals x squared that I have in red. Y equals 2, I have that horizontal line there. And then x equals 2, I have that vertical line there. Now the region with those 3 curves as its perimeter is this little triangular piece here. Now it might be hard to see, but in this case, this point is the square root of 2, comma 2. This point is 2, comma 2. And this point is 2, comma 4. I'm going to take this triangular piece and rotate it around the line y equals 0, which is just the x-axis. So as I do that, I'm going to create a figure with some space in the middle. Be careful when we go to integrate well, let me just draw it. My rectangles My outside rectangle goes from the top, which is y equals x squared, down to the line I'm rotating around, which is y equals 0. And then my inner rectangle is going to go from the bottom line, which is y equals 2, down to the line I'm rotating around, which is y equals 0. And if I do a disk method with the outside radius being the longer rectangle and the inside radius being the shorter rectangle, so disk method minus disk method, then I'll get what I want. But we have to be careful. Our bounds are going to be root 2 to 2 in terms of x values. My rectangles were oriented so that we're going to be integrating with respect to x on both cases. I mentioned that my bounds on x go from the square root of 2 up to 2. That will be the case for both situations, both the inside and the outside radius. The outside radius is going from the curve y equals x squared, so I'm going to use x squared, down to y equals 0, which is the x-axis, so down to 0. X squared minus 0, quantity squared. Make sure I have the quantity squared in there. So that gives me my disk method with the outside portions. And with the inside portions, the inside is going to go from y equals 2, as we saw, down to the line I'm rotating around, which is y equals 0. So we're going to end up with this. Now, plugging this in shouldn't be extremely difficult, I don't think. Plug in square root of 2 to 2, x squared minus 0 squared. You're going to get an ugly number. I'm going to just do the approximate case right now. So the first integration is approximately 5.2686 whatever times pi, which after I multiply times pi, I get roughly 16.55188,663 minus, well, when I integrate here, I end up with, whoops, I hit the wrong button, I apologize. 2.34 approximately times pi, which is about 7.361209,476. You could do this by hand if you'd like. And I believe you get some number times square root of 2. So if I wanted to do this and be exact, I think this 16.55 has pi and square root of 2 involved in it. And then I think this number also has pi and square root of 2 involved in it. I'm just using my calculator. So approximations are perfectly okay with me. But that becomes about 9.19 as my final value that I get by taking this region and rotating it around the x-axis. So again, if you wanted to, you could get the exact answer. The exact answer, again, is very messy because it involves this first one becomes pi. This first integration is that'd be 2 to the 5th over 5, so that'd be 32 over 5 minus root 2 to the 5th over 5. That would be 4 root 2 over 5. So that would be the first integration. That gives you about the 16, this one. And then if you did the second integration, that one's a little bit more straightforward. What you get is you get, oops, pi. When you plug in 2, you're going to get an 8. When you plug in root 2, you're going to get a 4 root 2. And that's where the 7.36 comes into play. So in any case, in my class, I'd ask you for the rounded version. And so just plugging these into your calculator is just fine. Now, one thing that I've been always doing is I've been setting these up as 2 integrations. You can, if you'd like, combine these 2 integrations into one if it makes more sense. So if you'd like to, then you can integrate. It's a little bit tricky again. We go x squared minus 0. I'll just leave it as x squared. Squared minus 2 squared. And integrate that whole thing with respect to x. So if you'd like to, you can combine that, these two, by just saying the argument is now this minus this. Make sure you square both pieces and you're not squaring just the subtraction of x squared minus 2, but you're squaring the x squared and you're squaring the 2 separately. And if you do that, then when you plug this in, might be a little bit easier. You can also, if you want, plug in this in one big line on your calculator and then get the final answer. So there's a number of ways to, plug this in. The setup is the more important part. And then there's a number of different ways to get down to the final approximate answer of about 9.19. So there you go. You can plug in this with one line on your calculator. If you like one integration, you can plug in one integration on your calculator. If you want to do things by hand, you can. If you just want to, plug this whole thing in and get a 9.19, that's fine too. Let's try another. Let's find the volume of the object made by revolving the region, which is bounded by y equals square root of x and y equals x squared around the x-axis. If you want to try this on your own, push pause on the video. In a couple of seconds, I will do this on my own. The region that we're looking at is bounded by y equals x squared, and y equals the square root of x. The square root of x is this curve. Y equals x squared is this parabola. You'll notice that the only bounded region, closed bounded region that we have is this one, which goes from 0, 0 up to 1, 1. So the x values are ranging from 0 to 1. So are the y values. But we want to rotate it around the x-axis. So as we rotate it around the x-axis, you'll notice that, again, in this region, my outside rectangle is going to go from the square root down to the x-axis. My inside rectangle goes from y equals x squared down to the x-axis. So outside goes from square root to the x-axis. The inside goes from x squared to the x-axis. And again, that's because my region looks like this. Okay. So there's my region, rotate around. By the way, we are going to have some holes in the middle. If you think about this, this is almost like a cup shape. And so we're going to get some holes in the middle. I am ready to do my calculations now. So we saw that since my rectangles are perpendicular to the x-axis is horizontal, I'm going to be integrating with respect to x. The x value bounds are 0 and 1. Those are going to be on both the inside radius and the outside radius. The outside radius goes from the square root of x down to 0. The inside radius is going to go from x squared down to 0, down to the x-axis, which again, x-axis is the line y equals 0. And then I just plug those things into my calculator. So when I plug those things into my calculator, you can do this again individually. You can do this as one line on your calculator. The first one gives me 0.5 times pi. I'll do this separately right now. The second one is going to give me, I believe, 0.2 times pi. I forgot to type that one in, but yeah, 0.2 times pi when I think about it. And so when I subtract, I would get that the volume of that object is 0.3 times pi. Which is about 0.94. So if you're doing approximate answers, you can get it at approximately 0.94. If you want to combine these integrations, feel free to do that as well into one. You can also, like I've been saying, you can type this whole thing into one line if you like. And if you only need the approximate, then you can just do that. But 0.94 or about 0.94, which is precisely 0.3 times pi. So that's the volume of this object. Now I did want to just show you this one We have obviously our region graphed, but I've graphed it in a three-dimensional plane now. And then we want to rotate that around the x-axis. So we're going to have a little bit of space in between here where, again, if it were a physical object, you could sort of, you know, put something in there, like stick a stick in there or put your finger in there. And what it's going to look like is this, but you'll see that this thing, again, is kind of bowl-shaped. Not a perfect bowl. The inside of the bowl has this curve to it, and the outside of the bowl is going to have this curve to it. So if you just look at here, it looks like a parabola figure. If you look at here, it looks like a parabola pointed the other direction. So this is the object we get. This is the object. So it's an interesting thing, but now we know that the volume of that thing is about 0.94 or 0.3 times pi if we wanted to be exact. So that's the thing in there. Let's look at another example. Let's do another example. Let's find the volume of the object made by revolving the region bounded by y equals 3 over 1 plus x, y equals 0, x equals 0, and x equals 3 around the line y equals 4. So we're going to find this value. The first thing I need to establish is where my region is at. We have y equals 3 over 1 plus x. That is this rational function that I've graphed here. Obviously, it has two sides to it. When I graph y equals 0, that's the x-axis. When I graph x equals 0, that's the y-axis. And then when I graph x equals 3, that's a vertical line right here. Now, the only region with all four of those as forming its perimeter, the only bounded region there with all four of these sides bounding the perimeter is this one in here. It goes from 0 to 3 in terms of x values. The top of the region is the y equals 3 over 1 plus x curve. The bottom of the region is y equals 0. I want to rotate that region around the curve y equals 4. And if I do that, if I rotate around y equals 4, then my rectangles, well, notice that my outside rectangle is going to start at the x-axis. So it's going to start at y equals 0, and it's going to go all the way up to y equals 4. So the radius of a outside disk is going to go from 0 to 4 or 4 to 0, however you like to say that. With the inside disk, the radius is going to go from 4 down to the curve y equals 3 over 1 plus x. These rectangles are vertical. And so we're going to be integrating with respect to x. And as we can see, my region goes from x bounds of 0 to x bounds of 3. So x from 0 to 3 when I integrate. Again, outside radius is from 4 to 0. Inside radius is from 4 down to 3 over 1 plus x. And that's how we set this up. Now I'm ready to do my setup. We know we're integrating with respect to x. Like we said, x bounds are going to go from 0 to 3. That's going to be on both the disk method with the outside radius and the disk method with the inside radius. So that's that. Again, outside radius, you could say you're going to go from y equals 0 to y equals 4. If you do 0 minus 4, technically your radius is negative. Squaring is going to fix that, so it's not a big deal. But usually what I do is I make my radius positive whenever I can. So I will write the outside radius as 4, y equals 4, down to y equals 0. So 4 minus 0. In a similar way, I'm going to make my inside radius 4 minus 3 over 1 plus x. Now, when I write this into my calculator, I tend to put parentheses around the 1 plus x, or else the calculator doesn't recognize the order of operations like I want it to. As long as I write things in correctly into my calculator, I can get the final answer. Now, in this case, my final answer is not a nice rational number. This 3 over 1 plus x throws off the numerical value I get. So I'm just going to type this as one big line into my calculator, or since we're integrating from 0 to 3 and then multiplying by pi, you could have also combined it into one integration and type that one big integration in on your calculator. So you could have done that as well. So whether you type it as 2 or as 1, just be careful that if you are typing as 1, this piece needs to be squared and this piece needs to be squared separately. In any case, what I got is about 83.32. That's after I multiplied by pi. That'd be 26.52 roughly before I multiplied by pi. So that would be the answer that I'm looking for. You can, if you'd like, do this by hand, but it's going to take essentially the tools we did with partial fractions. So we'd be integrating things and getting natural logs of stuff. But it is perfectly possible using the techniques that we've learned through integration to do this by hand. I just don't want to take the time to do that on this video. We'll do one more example. This will be the last example using the disk and the washer methods to find volumes of an object. We want to find the volume of an object made by revolving the region bounded by y equals 5 minus x, y equals 0, y equals 4, and x equals 0 around the line y equals 0. So around the y-axis. The, the x-axis, excuse me, I misspoke, the x-axis. Now, this is kind of nice because y equals 0 is one of the boundaries of my region. And therefore, hopefully I won't have a washer method. I'll just have one solid object when I rotate it around that x-axis. Let's go ahead and graph this region in 2 dimensions and then see what's going to happen when I revolve around y equals 0. When I draw this in 2 dimensions, what you'll notice is that when I draw the line y equals 5 minus x, that's this one, and then y equals 0, that's this one, x equals 0, that's this one, and then y equals 4, that's this one, I actually have 2 bounded regions. Now, the only one of those bounded regions that has each of the 4 lines as part of the perimeter is this in here. So if I were to shade it, it'd look like this. This is the region we're looking for. This is the only one that has all 4 of those as part of its perimeter. This is also bounded, but it only has 3 out of the 4 lines as the perimeter. We are going to rotate around the line y equals 0. In other words, the x-axis. Now you'll notice that on this one, I don't have a huge problem, really, but if I'm using x values over here, like let's say I use an x value of about 2.75, then the top of the radius of a disk, the top of the rectangle that I draw, is going to be at y equals 5 minus x, and the bottom is going to be at y equals 0. Very good. There's going to be no space when I rotate around the x-axis, and that's great. However, if I'm over here between 0 and 1, then the top of the rectangle, which is the radius of my disk, is at y equals 4, and the bottom of my rectangle is going to be at y equals 0. So in between 0 and 1, the calculation for this rectangle, which is the calculation for the radius of my disk, is different than when I go from 1 to 5. This is not going to be a huge problem. Basically, all we have to do is we have to calculate the volume of the object from 0 to 1, and then calculate the volume of the object from 1 to 5. And then together, those 2 values will add together to give me a single volume measurement. So there you go. That's how we're going to do this problem. Again, between 0 and 1, our rectangle goes from y equals 4 to y equals 0. From 1 to 5, our rectangle goes from y equals 5 minus x down to y equals 0. There's no holes, so this is just going to be a standard disk method without the washer piece. Now, what I would do, I don't know if I do this in 2 steps or 1 step, but what I would say is our bounds, if I wanted to find the volume going from 0 to 5, I actually have to break that integration up because we don't have a continuous function that gives me my radius of the disk. So what I would do is I would integrate from 0 to 1, find that value, and then integrate from 1 to 5 and find that value. Like I said, between 0 and 1, the top of the rectangle is y equals 4. The bottom of the rectangle is y equals 0. Between 1 and 5, the top of the rectangle is y equals 5 minus x. The bottom of the rectangle is y equals 0. That's what we end up doing. That's what we'll end up doing. The first integration, when you integrate, you end up with, I believe, 16. Yes, 16. That is 16 pi, excuse me. So don't forget about the pi out front. So 16 pi. And the second integration, when you integrate from 1 to 5, you take the 5 minus x minus 0 quantity squared, integrate that with respect to x. I get 21 and 1/3. That is times pi. If I wanted an exact answer, that's 37 1/3 times pi. If I want an approximate answer, that's about 117.29. So if our radius function is not, I can't write it as a single function. In other words, if that radius function, which again is just the length of the rectangles, is piecewise defined, like in this case, then I'm going to take one piece. In this case, I integrated from 0 to 1 to give me the one piece. To get the second piece, I had to integrate from 1 to 5. And that's it. That's the whole problem here. Obviously, things can get more complicated. You could have something like this object, but rotated around the line y equals -2. And that would, give slightly more complications. You just have to do a washer method from 0 to 1, and then another washer method from 1 to 5. So you can do all kinds of complex operations if you're rotating a region around either a vertical or a horizontal line. Just so that we have this one graphed in 3 dimensions, again, this is the region we're looking at, okay? And we rotate that around the x-axis, which is the line y equals 0. If you do that, the first part, from 1 to 5, gives you kind of this figure. From 0 to 1, you just get a nice cylinder. And what we're doing is essentially combining these. So we end up with this figure here. And we're saying that this figure here has volume of that 117.29 roughly. And again, you can imagine figuring out the volume of all kinds of figures. This one didn't have any hole in it, but you could have obviously, put a hole in it, done a lot of other things to it. Okay. So now we have ways to find volume of spinning a region around the x-axis. And we also could have spun this region around the y-axis as well. We would have just had to do our integration with respect to y. And in fact, in that case, we don't need to have two pieces because all of my radii would be defined in the same way. Again, don't worry about that right now though. But we could spin this region around the x-axis like we did. We could have also spun it around the y-axis. And we've done a couple of those earlier. That is the end of using the disk method to find value. In the next section, we'll find another way, but this is the end of this section, which is the disk method to find value.